Hi, I'm Joel Welling. This is a NIP project, so it's basically something unlike a traditional supercomputing application that we are trying to bring to supercomputing environment. I'm going to talk about automated learning from text. This is a project that's going on CMU and a lot of other places, I suppose. It is not currently a supercomputing problem, but it really ought to be. The way it works is that you have some corpus of text. The case in question here is ClueWeb, which is about 7 terabytes worth of web data, which was spidered down to CMU in 2009. You go over this with various statistical algorithms, learning algorithms like clustering and singular value decomposition. Basically, there are filters which are passed over the data, the web pages which have been downloaded. Those filters build. Are we all right? Oh,
no, we're all right.
Those filters build matrices from the original data, and then very large singular value decompositions and clustering algorithms are run on those matrices. What you're trying to do is simultaneously infer new patterns for these extraction filters and identify new data which matches those patterns. So it's kind of a double learning process. The largest scale projects are typically done using Hadoop or other MapReduce methods. Hadoop it's good for pouring large amounts of data from drive to drive, applying independent filtering operations on each, but it's not really good for anything that involves iteration or interaction between remote parts of that data. So we would like to move this to a supercomputing environment. The particular case we're looking at is NELL, the Never-Ending Language Learner. NELL is a project of the Read the Web group at Carnegie Mellon Computer Science. Tom Mitchell and William Cohen are the leaders of that group. It's based on this 500 million page web crawl called ClueWeb 2009. And if they have an assertion that they want to test, they will either use the web access APIs for search engines like Google and look up the corresponding facts. Like if you have a belief about something, you can download the Wikipedia page and see if the statistics of the Wikipedia page are in keeping with the statistics you expect. Or they'll just automatically submit jobs to Mechanical Turk and let some human at very low wages check the veracity of what they're saying. If you're interested in NELL, you can actually follow CMU NELL on Twitter. And NELL makes discoveries and then posts them. Some of them are fairly impressive, like, well, I mean, for appropriately chosen scales of impressive. NELL would think that plastic sugar bowl is an item you might find in the kitchen. But a lot of them come from very simple templates, like, I think Kazan River is a river. How did it know that? Well, it had a template that said that the word or noun phrase that comes before the word river is likely to be a river. And sometimes these things fail utterly, like, I think CL by laundry shoes is a kind of clothing. Problem is that it's identified CL by laundry as a single noun phrase, and it has associated it with shoes, so that was a bad fit to that particular template. So that's generally the way these things work. The way NELL does its task is to extract new instances of categories and relations, and add them to the knowledge base, and it's the engineering of the knowledge base we're going to talk about in just a second. And then, based on that knowledge base, every day it learns to read better because it's using that knowledge base to check its inferred patterns and inferred semantics for words back against the corpus of text. And there are multiple different algorithms which NELL uses simultaneously to, each of which contributes some probability to the truth of statements. And when the collective probability from all these algorithms is high enough, NELL will conclude that the statement is probably true. NELL learns by cycles. It started in January of 2010 and has been running continuously, or 2010, and it's been running continuously since then. Each cycle takes rather a long time because it requires pouring the entire corpus from disk to disk, applying the templates and checking against the known knowledge base each time. So this is basically an iterative algorithm where each iteration involves the file transfer of 7 terabytes of stuff. They also do periodic human supervision for reasons that are unclear when they just ran this algorithm. Some categories of knowledge NELL made very good, accurate discoveries about, and some categories it just did rather badly at. And it became necessary to prune out or correct the categories that it was doing badly at. So every so often, someone looks at the general new knowledge that's coming in and says, no, that is not actually a company that makes shoes. It's a misidentified noun phrase, something like that. Obviously, this whole disk-to-disk thing is slowing NELL down a lot. We would like to hold the whole corpus in memory, and we would like to learn the templates and facts simultaneously instead of in this iterative process. And then we could speed this whole learning thing up by a factor of 100 or more. When that happens, the knowledge base for NELL, which is around 500,000 insertions now, would be expected to grow on a much steeper curve, or 500,000 assertions now. In order to get scaling, in order to fit things into memory, there are some compromises which are done now. I just want to give you an example. If you have a document full of words, you can look at all adjacent groups of 5 words and find words that occur together. For example, you might find that shoe and lace tend to appear together. And then in a giant matrix which has all the words as the columns and all the words as the rows, you would put a tick mark in the column for shoe and the row for lace. And then afterwards, you can apply clustering algorithms, basically eigenvector identification algorithms on that matrix. The problem with this approach is that it's what's called a bag of words. It doesn't really distinguish between word order. For example, if you found the phrase, Bill ate the cow, you wouldn't be able to distinguish its statistics from the cow ate Bill. And obviously, semantically, they're very different. That is why the goal is to do deep learning, which, when we say deep reading of a document, we mean actually understanding each individual sentence, parsing it out, instead of just dealing with a bundle of data. And that's what we think will take so much more memory resource. Like most of these projects, academic CS projects, especially in machine learning, everything is written in Java. There's also a natural tendency to use outside web services. For example, as I said, if they want to check an assertion, they'll download the Wikipedia page. There's also some issues with the database implementation of the NELL knowledge base. That's the project we're working on now. And there's also a Hadoop-based mindset. We like to think about scaling in terms of having a big corpus of data in memory and running a lot of threads over it at the same time, using what we would think of as genuine scaling methods. They tend to think of everything as single-threaded and Hadoop-based and embarrassingly parallel. So just getting past that mindset is a little tricky. The current codes that they have, while Java-based, are single-threaded codes. And if they want to do things faster, they'll just run multiple separate JVMs, which of course means dividing up the memory space of the machine. How are we trying to get past this? Well, we have learned to run Java stably. That's actually trickier than you would have thought. Java is not normally considered a supercomputing programming language, but it can run just fine. We are trying to move to a scalable database. We're also going to have to minimize real-time web interaction, and I'm not sure how that can happen except by compromise with the groups. And once these things are in place, it should be relatively straightforward to modify the Java codes to do more of their tests and more of their optimization algorithms with parallel methods. But once again, we expect everything to run in a single Java virtual machine. The easiest thing to do is to run things in a shared environment, and that's why we're thinking Blacklight is such a good machine for this. It has a very large single memory space. I don't know who has tried to run Java on large shared memory machines out there, but there is an issue. The issue is that Java runs a garbage collector, and by default, it figures out how many cores there are on the machine and runs a garbage collection thread on every core. In the case of Blacklight, that's an awful lot of cores. And so while you might have 16 cores allocated to your job, I believe that Java will actually look in the proc directory, find out the total number of cores on the machine, and spin up that many garbage collection threads. So those garbage collection threads basically kill you. So you have to explicitly tell it how many garbage collection threads there are. There is a Java command line option for that. And you must force Java. Usually Java is spawned by some script because specifying the class path can be really verbose. You have to modify that script to get the right number of threads in there. There's a trick. There's a sub-trick here in that a very common Java database used both from Java and from Python is Lucene. Lucene is also written in Java, and if you have a program that fires up Java and then that program will fire up a Lucene server, if you haven't modified the code that starts up the Lucene server, Lucene will spawn all those extra garbage collection threads, and once again, you'll kill your job and possibly your machine. But one can get past this by tracing these things down and running the right number of threads. So, on to the knowledge base. The knowledge base, it holds the ontology. That is to say, what is what? A shoe is an article of clothing, is an object. And so it's a hierarchy, it's a directed graph of information. As the program runs, it's referenced continuously. So for example, if you have some group of words and you want to see if they fit a particular template, you would take the individual words, check them against the knowledge base, see if their generalizations fit the descriptions of the slots in the template. And so it actually gets an awful lot of traffic and is sort of the limiting rate, the rate limiting part of the execution of NELL. NELL's knowledge base is described in three ways. There's Theo. I don't know what Theo stands for, but it's the syntactic representation for this knowledge base, and it's sort of evolving under our feet. There's a TokyoCabinet representation. TokyoCabinet is the previous version, or it's a common, free, relatively fast key value store, and we're trying to move it to a graph database based on Neo4J. Why do we want to change? Well, the scaling should be better under Neo4J. TokyoCabinet doesn't have explicit transactions, and we need explicit transactions to get the parallelism right. And it looks like the graph database is a more natural representation for this. Here's a quick syntax for Theo. Any given question you might ask the database is an entity associated with a slot. And so you might say hair color. So the hair, let's see, let me say that differently. Bob hair color. If there's an entity named Bob, some person, the slot, the attribute of that entity would be Bob's hair color. And a belief is a query and the associated answer. So it's a query plus a value. Some entities are primitive, like Bob. Some entities are strings of other things, like well, you'll see examples. Bob hair color can also be an entity in its own right. The values of things are typically strings, but they can also be lists. For example, Tom and Sally might be entities in the database. The slot wife for Tom is occupied by Sally, and reflexively, Sally, the slot husband for Sally would be occupied by Tom. But we can also make statements about Sally's hair color in Theo. If for some reason Tom has more than one wife, then Tom's wife, Sally, has a hair color which would be blonde. But if we want to make a statement about all of Tom's wives or anyone who is Tom's wife without specifying Sally, we would say Tom's wife, hair color equals blonde. So notice that there's a difference between the two. And one of the great strengths of Theo is the ability to represent both ideas, the general concept and the specialized concept. Some beliefs are currently valid but are being dropped. At the moment, syntactically, you can say Tom equal blonde, but you really want to say Tom hair color equal blonde. You want that slot to be there, and it introduces an ambiguity, which is going to trip us up in a second. TokyoCabinet is fast and light. It's key value pair based, and the way it works is just the way it looks like. This is the reason that Theo evolved this way. It sort of co-evolved with the TokyoCabinet database. I would write if I wanted to represent the query Tom wife, I would write the key Tom wife, and the value associated with that would be the value returned by that query. And if I have a more elaborate string, like Tom wife hair color, that would also exist and have an associated value. Very often these values are actually lists, and those lists get stored as text strings in the database. For example, Tom wife hair color, blonde, probability 0.8. So we would like instead to do this in terms of a graph database. There are a number of those out there, but Neo4j seems to be the most popular. It's compact and flexible. It's not specialized for web applications. A lot of graph databases are designed to be run directly from web pages over JavaScript or JSON transactions, and that's not really what we want, obviously. It also has a pretty common architecture. There's a general architecture for graph databases called Tinkerpop blueprints. Gotta love those web names. And Neo4j pretty closely matches that. So if we decide at some later point we want to substitute a different graph database, it should be pretty much straightforward to slot it in. Graph databases consist of nodes, relationships, and properties. A node is simply, you might think of it as an entity, like there is a node associated with Tom, there is a node associated with his wife Sally, and in fact there are nodes associated with abstract relationships that have no specific names associated with them. A relationship is a connection between nodes. It's a directed thing. So while if the upper blue dot is Tom and the lower one is Sally, the forward-going relationship might be wife, but the inverse of that relationship might be husband, and in fact only one of them would actually exist in the database. If you wanted the husband relationship, you just traverse the wife relationship backwards. Properties are just collections of values. Typically, you would have a single value or a string, like a string or a float, or you might have an array of that same value type. And you would store things like the likelihoods of particular events or the type identifiers for nodes or the names of the entities for which those nodes are supposed to represent in the associated properties. So given a node, it's a one-step operation to get its relationships. It's a one-step operation to get its properties. Both of them are accessed by string names. Given a relationship, you can get the node at either end. There are also indices, so I can keep an index of all the entities, for example. And then if I want to find the entity for Tom, I can just say, look up the name Tom in that index, and it will give me the associated node. So this seemed like a very natural representation. When we started this project, it looked like everything would be simple. There are some issues, though, because the original Theo language was developed based on strings. The earlier version didn't really make a distinction between strings and entities. So, for example, if I said Tom's wife equals Sally, there was no syntactic way to tell whether Sally was to be regarded as some random string of data or Sally was to be regarded as that particular entity. It's also true that if I have multiple nodes that have properties, in principle, those properties, if I traverse over to those nodes, I should say that a traversal is a particular path through the directed graph, and they can be manipulated as separate entities. Separate traversals are entities in the graph database. If a traversal refers to more than one node, should I group the properties associated with that node as if they were the properties of the answer for that query, or should they be considered distinct? This is something which Theo never had to think about, so it's been ambiguous. Plus, the Read the Web group has, since we started this project, added the notion of contexts. So, for example, Tom's wife might be Sally for some particular interval, and it might be Anne for a different interval. So those time intervals are the context. They have a textual way of representing that in the TokyoCabinet database, but not so much in the graph database yet. So we have to compromise on what that means. Here's an example graph. The diamond-shaped node at the top is not something to think about. It's just the reference node for Neo4J that always exists. And it's not really a part of the description we're dealing with. Entity nodes have names associated with them, and they're shown in these graphs as rectangular boxes. Nodes that are associated with slots are shown as circles, and the relationships are identified by name, so that the entity node Hillary in this graph has a relationship hair color to the slot hair color, and because of this business of wanting to be able to distinguish general statements about hair color from specific people's hair color, we actually do two hair color links to get to the next entity node, which is associated with the word. So if you look at this same graph, there are two paths there. Bill Clinton, we got into Bill Clinton as being sort of the root entity node in our discussion, so please bear with me while we use that name. Bill Clinton has a dog, and that dog is named Rover, and Rover's hair is blonde, according to Tom. But if I want to make a general statement about Bill Clinton's dog and the hair color thereof, that would be the top two blue nodes followed by the green nodes. And I would then be able to say Bill Clinton's dog hair color is gray, according to Sam. And the fact that we have doubled up the nodes, made it two steps to make the dog link from Bill Clinton to Rover instead of just one, allows us to make the distinction between those two concepts. There are ambiguities in Theo which are causing us problems. For example, Bill Clinton should not actually be allowed to have attributes without names, or without slot names, but the current syntax does. So example, Bill Clinton's name is Bill's name, and that is the top two blue boxes, and no pairs of blue boxes should really exist without a circle in between. also isn't clear from the Theo syntax whether when I say two statements about things that are blonde, I mean the same entity for blonde. And if I do, then, for example, those two green boxes should actually be the same box in the graph. So what's the status of the project? Well, obviously we have the Java part licked. We are actually a little behind on the knowledge base project, I think, because the target is changing underneath us and because we've developed these or discovered these ambiguities. The good news is that this project is kind of reflecting back onto the structure of their knowledge base and the description of their Theo language. So we're actually helping the project in more than just supplying a faster and more parallel knowledge-based representation. An implementation exists. Once I have cleaned up these ambiguities, we need to do timing tests. And that's where I am.
Okay. Thank you, Joe.
Questions?
Questions? Anybody still there?
I'm still here.
It's Ralph. I have a question. Way back in the beginning, when you talked about a bag of words,
I like bag of worms better, but go on.
Yeah. I mean, if you have rows and columns, you could indicate word order by just populating the matrix unsymmetrically.
Yes.
Why don't you just do that?
Well, you only get adjacent. You could certainly do that, and then you'd have to change your numerical methods, but there still certainly would be clustering algorithms that would work. But it doesn't get you all the way to where you want to go. Like, if I have a sentence with some random clause in the middle of it separating the noun from the adjective that I want that noun to refer to, I'm not going to discover that relationship unless I actually parse the sentence and do its grammatical.
Sure. And in fact, if you ask a question, you invert word orders sometimes.
Yeah, exactly.
But I mean, it seems like you're just throwing away information by just doing it symmetrically.
Yeah, I think that's true. Nonetheless, this is the way they typically do it.
Okay.
I'm not sure whether they do it that way because they get a broader range of numerical algorithms by using symmetrical matrices, or I don't know. Obviously, there are other options.
Okay.
Questions? Okay. Well, not then. Thank you very much. We will put the proceedings here up on the website, including, I guess, the YouTube recording. So, which, by the way, I will now stop recording. And thank you very much, everybody, and we'll see you again next month. Bye-bye.
Bye.